Hello viewers, in this session we will touch upon Taylor's theorem, which shows that every analytic function actually has a power series representation around its point of analyticity with some radius of convergence. So, firstly we will start by showing that power series, given a power series, it is actually an analytic function. So, given power series within its radius of convergence is a analytic function, and then we will go on to show that show the Taylor's theorem that every analytic function, conversely every analytic function actually has Taylor's series, a power series representation. Okay. So, firstly continuing from the previous session, I want to emphasize that the determination of the radius of convergence of a given power series can actually be done by using either the root test or the ratio test, or what I will show you is called the Cauchy Hadamard's formula. The determination of the radius of convergence of a given power series can be done using the ratio or the root test. So, I mean those are two tests at least you can use to find the radius of convergence. So, and in case you are not able to determine the radius of convergence using these two, there is a Cauchy Hadamard formula which I will show you in a moment. So, this you are aware. So, here is an example of using the ratio test to determine the radius of convergence. So, here is an example. So, consider the series, the power series. So, sigma z power n by n factorial n from 0 through infinity. So, by ratio test, this series converges when absolutely when the limit as n tends to infinity of the modulus of the n plus 1th term. So, the n plus 1th term in this series is z power n plus 1 by n plus 1 factorial divided by z power n by n factorial, the nth term. The absolute value of the n plus 1th term divided by the absolute value of the nth term is strictly less than 1. But notice that the left hand side of this inequality is limit as n goes to infinity of mod z by. So, z power n cancels with z power n plus 1 for 1 power of z, and then you have n plus 1 in the denominator due to the n plus 1 factorial cancelling with n factorial for an n plus 1. And then so, this converges, this series converges absolutely when the limit of this quantity is strictly less than 1. But notice that the limit of that quantity is 0 no matter what z is. So, 0 is strictly less than 1 is always true. Independent of z is the point. So, independent of z, 0 is less than 1. So, what you have is that for any z belongs to C, this series, the given series converges absolutely, i.e., the radius of convergence, the radius of convergence is infinity. So, So, here we have actually used the ratio test to determine the radius of convergence of a given series. So, we will come back to this example for a different reason, but for now we can use ratio test to determine the radius of convergence. So, also we can use the root test whenever appropriate to determine the radius of convergence. Okay. And here is another way. I will provide the Cauchy's, or rather the Cauchy-Hadamard formula without proof. For radius of convergence. Okay, so, by slight modification of the proof of Cauchy's root test to determine convergence of series, we can actually give a proof for the Cauchy-Hadamard formula for radius of convergence. Okay. So, what it says is that the series sigma a n z power n, okay, has radius of convergence R, capital R, where R is given by, okay, R is given by 1 by R. Okay, so, it is given by 1 by R is equal to the lim sup of the nth root of absolute value, the modulus of a n. Okay. So, 1 by R is equal to the lim sup of nth root of a n. So, the viewer must be aware of what lim sup is from calculus of one real variable. So, if not, I will remind what it is. So, if you have a sequence a n, okay, so in this case complex sequence a n, okay, then you have a corresponding supremum sequence, okay, supremum of the set modulus of a n. So, I will use a different symbol here. So, if you have a complex sequence b n, let us say, then you have the supremum sequence modulus of b n, modulus of b n plus 1, etc., modulus of b n plus 2, so on. So, you consider the supremum of this set of the moduli of b n's where n greater than or equal to little n, okay, where j greater than or equal to little n. Okay. And then, so the supremum as this n varies, okay, that forms a sequence. Okay. So, what I mean by that is, the supremum sequence S n is equal to the supremum of modulus of b n or absolute value of b n plus 1, etc. This is S n plus 1 is equal to supremum of modulus of b n plus 1, modulus of b n plus 2, etc. Okay. So, so this sequence of S n's, okay, so this sequence S n is the supremum sequence. Okay. So, the lim sup of modulus of b n, let us say, okay, the lim sup of modulus of b n is actually the limit as n tends to infinity of S n. Okay. It is easy to see, well, notice this limit always exists. Okay. It could equal infinity sometimes. What that means is the supremum, the suprema are constantly infinity. Okay. So, it could equal infinity sometimes, but nevertheless this limit always exists, and that limit of these essence here, okay, is called the lim sup of the modulus of b n. Okay. So likewise, given this sequence a n, okay, we can construct the or we can find the lim sup of the sequence nth root of the modulus of a n, okay, and that is equal to 1 by the radius of convergence. Okay. So, here we have the usual agreement that 1 by 0 is actually infinity and 1 by infinity is actually 0. Okay. So, with that agreement on these two radii of convergence, okay, we have a formula for radius of convergence given by this equation. Okay, that is called the Cauchy Hadamard formula. I am not going to give a proof of this here. So, that is about the determination of the radius of convergence of a power series. Now, let us actually show that power series are actually analytic within their radius of convergence. Okay. So, in order to show that, first I am going to need a little lemma. Okay. So, we will start showing that power series with positive radius of convergence are analytic, All right. So, first we will need the following lemma. Okay. So, first I will show that the power series sigma C n z power n and sigma n C n z power n minus 1, okay, have the same radius of convergence. Okay. So, firstly note that given note that I am dealing with series of type 1, power series of type 1 with 0 as the center of this series. Okay. So, these are power series around 0, and also note that it would be a candidate for the derivative of a power series is actually differentiating this power series term by term. What I mean by that is, you consider the term C n z power n, its differentiation is n C n z power n minus 1. Okay. So, it would be really convenient if this term by term differentiation of the terms in this series is actually equal to the derivative of the power series itself. Okay. And what we are going to show is that that is indeed true, okay, within the radius of convergence for a given power series. Okay. So, with that as a goal, we first start by showing that the term by term differentiation of the power series. Okay. So, the series obtained by term by term differentiation of the terms in the power series and the power series itself have the same radius of convergence. Okay. So, that is the statement of this lemma, this C n z power n sigma, okay, and n C n z power n minus 1 within the sigma, these two have the same radius of convergence. Okay. So, so once again to emphasize, this is the derivative of this term. Okay. So, so let us prove this. So, the proof of this is as follows. First, if this converges absolutely, so which is within the radius of convergence, if this converges for modulus of z less than r, okay, then choose rho, okay, such that modulus of z less than rho less than r. Okay. And so, you are choosing a rho between the modulus of z and the radius of convergence, okay, and assume z not equal to 0, because I am going to divide by z. Okay. So, then the modulus of the nth term here. Okay. So, this is the nth term in this series. Okay, in this series. Okay. So, the modulus of this is equal to n by mod z, okay, times mod z by rho power n times modulus of C n rho power n. Okay. So, I am just rewriting the term within the modulus, okay, in that fashion. And the point here is that modulus of z by rho is actually strictly less than 1. Okay. So, I can use that to consider a certain geometric series. Okay. So, since modulus of z by rho is actually less than 1, okay, the series sigma n modulus of z by rho power n, okay, is not exactly a geometric series, but by comparison with by ratio test, for example, okay, you can show that this is convergent. Okay. So, sigma n mod z by rho power n, okay, is convergent, absolutely convergent actually. Okay. So, is convergent by ratio test, for example, right, because ratio test tells you that the limit as n goes to infinity of the n plus 1th term here, okay, which is n plus 1 modulus of z by rho power n plus 1 divided by n times mod z by rho power n, okay, is actually equal to limit as n goes to infinity of n plus 1 by n times mod z by rho. Okay. And mod z by rho is strictly less than 1. Okay. So, well, the modulus of this, or the absolute value of this. So, the absolute value of this and the absolute value of this. Okay. So, the modulus of z by rho is less than 1, modulus of z by rho is less than 1. Okay. And then limit as n goes to infinity of n plus 1 by n is equal to 1. Okay. So, all in all, this limit is strictly less than 1. Okay. And so, by ratio test this converges, this series converges. Okay. So, that series converges. So, we will use a property which we saw in the last session, that if a series converges absolutely, okay, then every term in that series is actually bounded by some constant. Okay. So, there is an m positive, okay, such that sigma n or I apologize, each term in the series. So, n mod z by rho power n, okay, is less than or equal to m for all n, for all positive integers, okay, for all n greater than or equal to 0, I will say. Okay. So, therefore, by the above I will call this star. Okay. So, by star, what we can say is that the modulus of n C n z power n minus 1. Okay. Let me go back to star. Okay. So, that is, so I have clubbed these terms. So, I have clubbed these terms. Okay. So, the modulus of n C n z power n minus 1 is less than or equal to m times, or m by mod z times modulus of C n rho power n. Let me make sure, C n rho power n or C n rho I apologize, in this star this should be rho power n here, not C n rho whole power n. Okay. So, this is C n rho power n. Okay. So, now notice that comparison test. Firstly, these are nth terms of a convergent series, because rho is within the radius of convergence. Rho is strictly less than capital R, and so m by mod z C n rho power n is absolutely convergent. Okay. So, now by comparison test sigma n C n z power n minus 1 is absolutely convergent. Right. This term is less than or equal to, I mean, in absolute value is less than or equal to the absolute value of a term which belongs to a absolutely convergent series. So, by comparison test this itself is, this series is absolutely convergent. Okay. So, we have shown that if sigma C n z power n is absolutely convergent, then the derived series sigma n C n z power n minus 1 is also absolutely convergent. Okay. Now, in the other direction also it is easy. Okay. So, now if sigma n C n z power n minus 1 is absolutely convergent, okay, we want to show that sigma C n z power n converges. Okay. So, then the modulus of C n z power n, we will estimate this, the nth term in the original series. Okay. This is less than or equal to modulus of z times the modulus of n C n z power n minus 1, okay, for n greater than or equal to 1, let us say. Okay. And so, by comparison test, okay, so by comparison test, this is the nth term of a convergent series, and then you are multiplying it by mod z, okay, which is a fixed number for a given z. So, by comparison test sigma C n z power n converges absolutely. That is easy. Okay. So, that completes the proof of this lemma. Okay. Notice that you could not have proved this lemma directly by using some kind of limit comparison test. Okay. So, that kind of test fails. So, you have to actually go through this kind of proof for this lemma. Okay. So, now we know that the derived series n C n z power n minus 1 of sigma C n z power n, okay, has the same radius of convergence. Okay. So, next what I will do is I will show using this that power series are actually analytic within their radius of convergence. Okay. So, then we can announce that power series are examples of analytic functions. Okay. So, here is the theorem. So, theorem differentiation of power series. So, let f of z equals sigma C n z power n, okay, and assume that this power series has radius of convergence r strictly greater than 0. So, we want a power series with positive radius of convergence. Okay. So, then f is analytic on B 0 R. That is the conclusion. Okay. And moreover, and the differentiation of f has a definite formula. It is equal to sigma n equals 1 through infinity of n C n z power n minus 1. Okay. So, term by term differentiation works, and that is the derivative of f, where f is a power series within the radius of convergence. Okay. So, for this is true for modulus of z strictly less than r, i.e., in the radius of in the disk of convergence. Okay. Notice that this statement once again is a statement about series of power series of type 1, and a very similar parallel statement holds for power series of type 2. Okay. So, you can modify the statement just by putting z minus a, okay, and assuming that the instead of z, and assuming that the series power series is about a point of analyticity, or is about a point a in the complex plane. Okay. So, a similar theorem can be stated for series of type 2. Okay. Nevertheless, we are going to prove this version. Okay. So, proof firstly by previous lemma. Okay. It since the derived series this sigma n C n z power n minus 1 and this series itself sigma C n z power n have the same radius of convergence. Okay. So, what we can do is by previous lemma, what we can do is we can define, okay, we can define g of z is equal to sigma n equals 1 through infinity of n C n z power n minus 1 for modulus of z strictly less than r. Okay. So, this definition makes sense by previous lemma. Okay. We can define because this series converges and it converges with the same radius of convergence. Okay. So, then now what we want to show, okay, so I will put this in parentheses. What we want to show is that this g of z is indeed f prime of z. Okay. So, we want to show that f prime of z exists, okay, and equals g of z for or within the radius or disk of convergence. Okay. So, then what we need to do is actually estimate the difference quotient of f and the difference of the difference quotient of f and the function g of z. Okay. So, for z comma z plus h within the radius of convergence or the disk of convergence rather. Okay. We will consider the expression f of z plus h minus f of z by h, which is the difference quotient of f, okay, at the point z, and then its difference with g of z. Okay. So, this this subtraction gives you, what does it give you? It gives you, well, what is f of z plus h? It is sigma n equals 0 through infinity. I will just write everything C n z plus h power n, okay, minus sigma n equals 0 through infinity C n z power n divided by h minus and then you have g of z, which is sigma n equals 1 through infinity of n C n z power n minus 1. Okay. So, this is in turn equal to, well, observe that in the numerator for the difference quotient, the 0 terms are C 0 and C 0 respectively. So, both those cancel each other. So, you can actually begin the the difference from the index n equals 1. Okay. So, this becomes sigma n equals 1 through infinity, okay, of C n, okay, times z power z plus h power n minus z power n, okay, and then divided by h minus all this minus sigma n equals 1 through infinity n C n z power n minus 1. Okay. So, this in turn is equal to sigma n equals 1 through infinity. I can take the division by h into the series. Okay. So, what I have is C n times, also notice that now both the series here begin with the index n equals 1. So, I will take the summation, since both of them are convergent series, I can take the summation altogether at once and then factor out a C n. So, what I have is z plus h power n minus z divided by h and then minus n c n rather z power n minus 1. So, that is what it boils down to. Okay. And then further continuing, so continuing this, what I have is sigma n equals this is equal to n equals 2 through infinity C n times z plus h power n minus z by h minus n z power n minus 1, because when n equals 1, okay, what I have is h by h on for this term. Okay. So, I have h by h for this term, which is 1, and then I have n equals 1. So, this is 1 times z power 0, which is 1. So, 1 minus 1 is 0. So, the index n equals 1 does not really give me anything, it gives 0. So, I can start the index from n equals 2. We will see, we will use this later. Okay. So, we will store this estimate for the difference between the difference quotient of f and g of z. Okay. Now, we will use the binomial expansion. Okay. So, by using binomial expansion for z plus h power n, okay, for n greater than or equal to 2, okay, z plus h power n, okay, is equal to sigma k equals 0 through infinity or 0 through n rather, n choose k z power n minus k times h power k. Okay. So, please note that we have not actually proved that binomial expansion works for complex numbers. Okay. But once again notice that the binomial expansion is actually an arithmetic property, okay, which works even for complex numbers, like it worked for binomial expansion of real numbers or real binomials. Okay. So, one can if the viewer is interested, one can actually prove this for complex numbers, okay, like one has done for real numbers, okay, or real binomials. Okay. So, so it does hold for complex numbers as well, and you can expand z plus h power n like that using binomial expansion. Okay. So, we will use this form, and what we get is z plus h power n minus z power n divided by h minus n z power n minus 1, which occurs here in our estimate, Okay. This is equal to, okay, this is equal to z power n, for lack of space. Okay. This is equal to z power n plus n choose 1 z power n minus 1 h etcetera plus so on until n choose n h power n, okay, minus there is a z power n in the numerator divided by h minus n z power n minus 1. So, this is equal to the z power n's cancel, okay, and then I can also divide the expression in the numerator by h. I can cancel one factor of h, okay, h is not equal to 0. Okay. So, what I have is n choose 1. Okay. So, I have n z power n minus 1, okay, plus n choose 2 z power n minus 2 times h plus so on, okay, and then I have n choose n which is 1, okay, h power n minus 1. Okay, and then I have a minus n z power n minus 1 which is here. Okay. So, now once again the n z power n minus 1 cancels, and what I have is, and this equals, well, the n z power n minus 1 cancels, and this equals n choose 2 z power n minus 2 h plus so on. Okay. So, I will write one more term, n choose 3 z power n minus 3 h squared so on until h power n minus 1. So, I can factor out a h, and what I have is h times sigma. I will write in terms of sigma. This is r starts from, I will have an index r starts from 0 and goes until n minus 2 of n factorial divided by n minus r plus 2 factorial, okay, and r plus 2 factorial, okay, times h power r and z power n minus r, or actually n minus 2 minus r. Okay. So, so for example, when r equals 0, you get n factorial by n minus 2 factorial times r plus 2 factorial, which is your n choose, or 0 plus 2 factorial, which is 2 factorial. So, you get n factorial by n minus 2 factorial times 2 factorial, which is n choose 2, and then h power 0 z power n minus 2. Okay. So, so you get back your expression here, okay, and you can write the estimate in this form, okay, or a term within the estimate in this form. Okay. So, now the estimate of the difference quotient f of z plus h minus f of z divided by h minus g of z in modulus, this is equal to the modulus of sigma n equals 2 through infinity of C n times h times. So, everything in the parentheses now is h times sigma r equals 0 through n minus 2 of n factorial divided by n minus r plus 2 factorial, okay, times r plus 2 factorial times h power r times z power n minus 2 minus r. Okay, please bear with me, there is a parenthesis there, and then an additional parenthesis and an absolute value sign. Okay. So, this is now this can be this is less than or equal to sigma n equals 2 through infinity, okay, of the modulus of C n and modulus of h, okay, times sigma r equals 0 through n minus 2, okay, of n factorial divided by n minus r plus 2 factorial times r plus 2 factorial, okay, times modulus of h power r modulus of z power n minus 2 minus r. Okay. So, from here, from the previous step to this step, what I have used is actually an infinite version of triangle inequality. Okay. So, it is an exercise to the viewer to actually prove that whenever the series A n is convergent, sigma A n is convergent, sigma A n equals 1 through infinity or 0 through infinity is less than or equal to sigma of absolute value or the modulus of n equals 0 through infinity. Or sigma of the modulus of A n, where sigma runs from n equals 0 through infinity. Okay. So, using this form of infinite version of triangle inequality, okay, using partial sums one can prove this. So, this is an exercise. Okay. Using this we can go from the previous step to this step, okay. And further this expression is less than or equal to modulus of h. I will pull out a modulus of h from this sigma n equals 2 through infinity of modulus of C n times then again I have n times n minus 1. I am pulling out an n times n minus 1 from this n factorial in the numerator. Okay. So, I am pulling out an n times n minus 1. So, what I will be left with is n minus 2 factorial. Okay. So, here is n minus 2 factorial within the sigma r equals 0 through n minus 2 factorial times I will rewrite the denominator as of n minus r plus 2 factorial as n minus 2 minus r factorial. Okay. And since I have a less than or equal to here, okay, so I will emphasize I have a less than or equal to. So, what I will do is I am actually lessen the denominator. So, I will write r factorial here instead of r plus 2 factorial. Okay. So, then I can write mod h power r here and modulus of n minus 2 minus r here. Okay. So, r plus 2 factorial is greater than r factorial. So, 1 by r plus 2 factorial is less than or equal to 1 by r factorial. So, I am using that to come to the this step here. Okay. And then this in turn is equal to the modulus of h times the modulus n equals 2 through infinity modulus of C n times n minus 1, and then what I have here, okay, what I have within this sigma you will observe is modulus of z plus modulus of h power n minus 2 by binomial expansion. Okay. So, this is nothing but the modulus of z plus modulus of h power n minus 2. For a given z, choose rho with mod z strictly less than rho strictly less than r. Okay. So, that modulus of z plus h also stays within that rho. Okay. Modulus of z plus modulus of h is strictly less than r rho whenever modulus of h is less than rho minus mod z. Okay. So, then by two applications of previous lemma of the lemma that we have proved, okay, of the previous lemma, okay, sigma n equals 2 through infinity modulus of C n times n minus 1 rho power n minus 2, okay, has the same radius of convergence, okay, converges to a constant, okay, and it is important that that constant is independent of h, a constant independent of h. Okay. So, the previous lemma tells you that if modulus C n z power n, okay, or sigma C n z power n converges, then the derived series sigma n C n z power n minus 1 also converges within the radius of convergence. Okay. So, since rho, the real number rho occurs within the radius of convergence, it is less than r. Okay. C n rho power n sigma of that converges. Okay. So, by the previous lemma n C n rho power n minus 1, and once again using that lemma n times n minus 1 C n rho power n minus 2, okay, also converge, both those converge within the radius of convergence when rho is actually strictly less than r. Okay, they converge absolutely. Okay, and they converge independent of this h, because there is no appearance of h in this series at all. Okay, so in the series sigma modulus of C n n times n minus 1 rho power n minus 2. Okay, so that is independent of h. Okay, so that is important. Okay, so the above. Okay, so modulus of h sigma n equals 2 through infinity of modulus of C n n times n minus 1 modulus of z plus modulus of h power n minus 2, which is our estimate of what we want. Okay, is less than or equal to modulus of h sigma n equals 2 through infinity modulus of C n, okay, n times n minus 1 rho power n minus 2. Okay, and since we have a multiplication by mod h of a convergent series, okay, of a convergent series whose convergence does not depend on h, or whose value is independent of h. Okay, and since modulus of so what I can conclude is, as modulus of h tends to 0, the RHS tends to 0. So, LHS tends to 0 as modulus of h tends to 0. Okay. So, the LHS tends to 0, LHS of this inequality. So, by RHS and LHS I mean the sides of this inequality above. Okay. So, since the LHS tends to 0, which is the estimate of modulus of f of z plus h minus f of z by h minus g of z, since this is, I mean, the above is an estimate of this, this tends to 0 as modulus of h tends to 0. Okay. So, we conclude that f is differentiable, okay, at z, okay, and f prime of z is equal to g of z when the modulus of z is strictly less than r. Okay. So, that proves this theorem, and that shows that power series are analytic within their radius of convergence, and their differentiation is precisely the term by term differentiation of the terms within the series. Okay. So, and then in the next session we are actually going to prove that every analytic function actually has a local expression as a power series. Okay, that is the Taylor's theorem, and we will cover that in the next session.